The next transfer function that we will consider is a transfer function that has a real pole not at the origin. And the transfer function that has a real pole not at the origin should always be written in this form. And we use this form because it makes the sketching of such a transfer function easy, or the Bode plot of such a transfer function easy. So it's 1 over 1 plus 1 over omega b s. And this omega b is what we call the break frequency. If I can give you an example of a real transfer function that has a real pole not at the origin, well, let's say it looks something like this: 4 over s plus 4. And to write it into that form, we can manipulate it by dividing top and bottom by 4. So that will be, well, let's write the constant first. Okay. Well, of course, not all of them look like this. We've got a 4 here and a 4 there. So say we've got something that looks like this: 1 over s plus 4. Well, we can manipulate it into that form as well by just multiplying top and bottom by a quarter. So it will be, let's write the constant first again, so it's 1 plus. Okay. So we will look at how to sketch something like this. But what if we want to sketch something like this? Well, again, because we are plotting in the log domain, we can interpret this as 1 over 4 times 1 over 1 plus 1 over 4. Yes. And the Bode plots for this means, or the Bode plots that we will do, then we can interpret this as we can add the Bode plot for a quarter, which is just a constant, to the Bode plot of this transfer function that has a real pole not at the origin. Okay, I'm going to delete this just for space. Okay. So of course the first step is to set s equal to j omega. Let's use the subscript 5. Okay, 1 over j omega over omega b. Again, we want to get this into the standard complex form of a plus gab, and to do that it requires a little bit of maths. We can multiply this by the complex conjugate. Okay, and we can break that up into 1 over 1 plus omega squared over omega b squared minus omega over omega b over 1 plus omega squared omega b squared times j. So that's in the form of a plus jb. Okay. Next step, what we have to do is we have to take the magnitude of that transfer function. And of course that requires us to the square root of the real part, that is the real part, and that's the imaginary part. So real part okay, and we can collect that over one denominator. Okay, and we can cancel some terms here. We can cancel that and that. And we are left with 1 over 1 plus omega over omega b, that's squared and that's squared. Okay, that is the magnitude. For the Bode plot, I'm going to already take the 20 log of that. So if we take 20 log of the magnitude of the frequency response transfer function, well, that just becomes 20 log minus 20 log of the denominator okay, and this part is obviously 0, so we are left with negative 20 log of 1 plus omega squared over omega b squared. Okay, we can also do the phase. Yeah, I've got enough space. Recall that our frequency response transfer function looked like that. So if we want to take the angle of that, well, that's just the arctangent of the imaginary part, which is that part. So that will be negative omega over omega b divided by 1 plus omega squared over omega b squared, and that all divided by the real part, that's 1 over that same denominator. Okay, we see we've got the same denominator here in both top and bottom, so that can cancel. So we're left with the arctangent of negative omega over omega b. Okay. So to make it easier on ourselves, I'm going to copy this, and I'm going to copy this, and let's start on a new page. Oh. Oh, wait. Sorry about that. Let's just put that over here. Okay, that was 20 log of the frequency response transfer function. And that was the angle. Oh, sorry, I see I copied the wrong. Okay. So let's start drawing our Bode magnitude and phase plots. I have to keep our space in mind. Let's do it next to one another. Okay. So this is the magnitude plot. And this is the angle. Okay, for this magnitude and phase, we have to consider three cases. We have to consider the first case when omega is much smaller than omega b, the break frequency. We can interpret this as omega tends towards 0. Okay. In this case, if omega is much smaller than omega b, and if we look at the magnitude, if omega is much smaller than omega b, that term is very small. That means this 1 dominates this function, which means our magnitude is negative 20 log of root 1. And that is approximately equal to, well, 0. And our phase, so, okay, so for, let's just put our omega b, let's do it at the top. For our phase, so for small frequencies, or frequencies much smaller than omega b, our magnitude will be 0. So we can plot it a point approximately for very small frequencies over there. Okay, and for the phase, well, if omega is much smaller than omega b, that will become a 0. Okay. And that means our phase is, so phase is just the arctangent of 0, and that is just 0. So for very small frequencies, our phase will go approximately through that point. Okay, the second case, it's when we consider when omega is equal to omega b. So when that is true, well then omega over omega b is equal to 1. So if we go to our magnitude, then well that goes to 1, this term. And that means our magnitude is negative 20 log of root 2. And that's approximately equal to minus 3 dB, if you go work that out. Okay, so remember this is the decibel scale, so negative 3 dB will approximately go through there. So our magnitude will start off going through that point, and then it will go through that negative 3 dB point at omega b. The phase, well, if omega is equal to omega b, then this will again go to 1, and that means our phase is just the arctangent of negative 1, and that is equal to negative 45 degrees. Okay, so we can make a point here for when omega is equal to omega b. So let's say that's approximately equal to the negative 45 degrees. So our phase will at small frequencies go through that point, and when omega is equal to omega b, it will go through that point. The third case we have to consider is when omega is much larger than the break frequency. So that's when omega tends towards infinity. Okay, if that is the case, well, if you go look at our magnitude function, then if omega is much larger than this omega b, this term dominates this function. So the 1 is relatively or comparatively small, so our magnitude function just becomes negative 20 log of omega over omega b. Okay. So to evaluate this, we can say, all right, but what if omega is equal to omega b? Well, then that value, this just becomes negative 20 log of 1, and that is just 0. If omega is equal to, say, 10 times the omega b frequency, well, then that just becomes negative log of 10, and that is negative 20 decibels. If an omega is equal to 100 times the break frequency, then our magnitude just becomes sorry, that should be negative 20, eh? So this becomes negative 40 dB. Okay, so we see that for frequencies where omega is much larger than omega, if it starts off at omega b, it is equal to 0, but then drops off by 20 decibels per decade. Sorry, let's do it like this. So we know that, so that's a phase. So we know that at, say, 10 times omega b, it will be negative 20 decibels, and at 100 times omega b, it will be negative 40 decibels. Okay, so before we draw that, let's do the phase first. So if omega is much larger than omega b, our phase function just becomes, if omega is much larger than omega b, then that becomes negative infinity. So that is minus 90 degrees. So if omega is much larger than omega b, so we can use a large, just put it large, so that becomes negative 90 degrees. So our phase plot will go through somewhere there. Okay. So before we draw the straight line approximation, we can see that our plot or magnitude plot will look something, let's use a color, will look something like this. It will, for low frequency, it will be 0 dB, and then at omega b it will be negative 3 dB, and then it will drop off with a straight line of a gradient negative 20 dBs per decade. With a phase plot, well, we know it's zero phase, or zero degrees for small frequencies. At omega b, the phase is negative 45 degrees, and for omega much larger than omega b, the phase is negative 90 degrees. Okay, so the straight line approximation of this will be, for the magnitude plot, will be, well, we can draw a straight line up to omega b, and then from omega b there will be a drop off of negative 20 dBs per decade. But the phase plot is a little bit more tricky. We have to estimate the points where the phase plot breaks away from the 0 degree line. And to do that, we can just find the points 1 over 10 omega naught. Well, let's write it to be clear. 1 over or a tenth of the break frequency, and 10 times the break frequency. The reason why we can do that approximation is because we know that for small frequencies, we know that the phase angle is 0, and for very large frequencies the phase angle is minus 90 degrees. And if we plug in 1 over 10 omega b into our phase equation, into that equation, we can see that it's approximately 0 degrees, and if we plug in 10 omega b, we can see that the phase is approximately minus 90 degrees. Okay, so the straight line approximation for our phase will then just be a straight line up to 1 over 10 omega b, and then it will drop off till the negative 90 degree line up to 10 omega b, and then it will continue on the negative 90 degree line. And that completes the magnitude and phase plots for a real pole not at the origin. So next time you get a transfer function that has a real pole not at the origin, you know that its magnitude plot will be for very low frequencies up to the break frequency. It will have a 0 decibel magnitude, and then after the break frequency it will drop off by negative 20 decibel per decade. With the phase, you know that for a transfer function with a real pole knot at the origin, you can approximate it with 3 lines, where the first line, it has 0 degree phase up to about a tenth of the break frequency, and then it will drop off till the negative 90 degrees up to 10 times the break frequency, and then it will continue on with a negative 90 degree phase, a constant negative 90 degrees phase. Alright.